Yes, welcome all at our weekly TCS seminar at Jagiellonian. Our speaker today is Csaba Tóth from California State, Northridge campus. Well, Csaba is well known for his contributions in computational and combinatorial geometry, specifically his work on Euclidean spanners and Steiner trees. I've seen various online setups of these problems and some sparsification setups as well. Today, as we see already, we will see a talk about optimal spanners in this Euclidean space and Euclidean spaces. Thank you, Csaba, for joining us today. And yeah, take it from here. The floor is yours.
So thank you for the opportunity to speak here. So I've been working on spanners for only the last couple of years. But let me start with a geometric properties. But let me start with a general introduction to spanners that probably many of you are familiar with. So spanners are defined for graphs in general. Even a weighted graph, edge-weighted graph, as a T-spanner is a subgraph of G, where we require that it approximates the graph distance up to a factor of T, distortion of T, or T is often called a stretch factor. So there's a distance in graph G between any two vertices, and the spanner should approximate it up to a factor of T. So in particular, it's a spanning graph. And a lot of work has been done for just unweighted graphs. And in this regime, the stretch factor in general cannot be better than 3. So the easy example to see this is the bipartite graph, where complete bipartite graph, when we delete any one of the edges, then the shortest path between the two vertices would be length 3. So that immediately gives a factor 3. And in general, in this general setting, a 2k minus 1 spanner can be achieved with this exponent. So it's super linear, but the exponent goes to 1 as k increases. And this is conjectured to be optimal pending Erdős's Girth conjecture. So this regime is well understood. What I'm talking about today is the geometric setting, where so this is another large area of spanners, where the vertices are a finite point set in a metric space, and the initial graph is the complete graph. So every edge is allowed, and the goal is to have a sparse spanner that still approximates the distances within. So essentially, it approximates the metric distances up to a factor T. 2 parameters have been studied for spanners in general. One is sparsity. This is just the size of the spanner. So the number of edges to number of vertices. And for weighted spanners, the lightness is the other important parameter. That's the total weight of the spanner compared to the not the total weight of the graph, but to the MST. So I'm not going to say more about the general graph setting. The entire talk will focus on the geometric setting. And the metric space will be d-dimensional Euclidean space in almost all of the results. So the first question is that what is the best we can say about sparsity in Euclidean spanners? And as opposed to the general graph settings, here here the stretch could be arbitrarily close to 1. So for any epsilon, one can find the 1 plus epsilon spanner, which is also sparse. So this is just a brief one slide summary of history. So Chu showed in the 1980s that Delaunay graphs attain a constant stretch vector in Euclidean space. Then in 87, Clarkson and Kyle independently proved that one can actually find the 1 plus epsilon spanner, which is already constant sparse, and so not this is the sparsity, not stretch, and the question was since then, what is the dependence on epsilon of the sparsity? So one other issue that has been raised several times, that if we insist on planar spanners in 2 dimensions, so the edges should not cross, what is the best possible spanning ratio there? Then there's a limit of some constant. The Delaunay triangulation seems to be a good candidate, but if we want to be really close to 1 plus epsilon stretch factor, then of course it's not the graph not going to be a planar graph in 2D, and this doesn't even make sense for higher dimensions. So so the best dependence on epsilon was already determined 4 years ago, but with the matching upper and lower bounds. So the lower bound was proven by Hungry and Shea Solomon. So that's a success story. What do we know about lightness? So it was known for a long time that a greedy spanner, that I will get back to soon, how exactly it's constructed, is a constant lightness. So the weight is comparable to the MST, constant factor of the MST, for constant epsilon. So for a long time, people were just happy with this kind of bounds, that for constant epsilon, the lightness is constant. But then more recently, after question raised by Rao and Smith, it's also interesting how exactly this constant depends on epsilon. So one breakthrough was this epsilon to the minus 2D bound that was originally proved in the 90s by Narashian and Smith. But then they wrote a book about geometric spanners that where an entire chapter went into the proof of this upper bound for lightness. So it wasn't easy, and it also wasn't tight. It was generalized to doubling dimensions later, and then there was an improvement. So the same epsilon, the big of the bound holds for doubling dimension, and the upper bound is again in this lower right corner here by Hungry and Shea Solomon. So it's roughly epsilon to the minus d. So so as you can see, there's almost matching upper and lower bounds for both sparsity and lightness. So you can ask, what am I talking about today if there are tight bounds? So let me just add two comments. One is the explanation for these algorithms in the upper bounds. So I'd like to explain what theta graphs are, because it's going to be relevant later, and what greedy spanners are. That are not difficult, but it's good to know. So again, these are classical constructions. So what are theta graphs? So theta is corresponds to an angle. So in the planar version, we are given a set of endpoints in the plane, And we want to build, so our graph is the complete graph, the weights are the Euclidean lengths, and we want to construct a spanner. So we start with an empty graph and we want to add edges one by one. How? Well, for each point, we partition the entire plane into cones, as pictured here, where each cone has 2 pi over k angle, central angle. So this is the theta refers to that angle of these cones. And in each cone, we find the closest point to P. So closest is in a polyhedral metric where you just sweep the cone with a line orthogonal to the axis of symmetry and find the closest point. So this polyhedral metric is helpful for computation. One can use data structures to find this closest point more efficiently than the Euclidean closest. And so that's just the construction, and then it comes with a proof that's also from the classical result that if the number of cones is 1 over epsilon, then this gives a 1 plus epsilon spanner. Yeah, so what I didn't say that we do this for every point, not just for one point. And then we get a spanner. The other comment down here is that, yeah, so I explained the theta graphs for the plane. The same idea works in any dimension. The dimensions, the only difference is that if we use, so first of all, it's not only a partition of the space into cones, but a covering, and the number of cones goes up with the dimension. So if you want a central angle of roughly 1 over k, then the number of cones is k to the d minus 1, and that gives this bound for the sparsity, which turns out to be optimal. So the other classical algorithm I want to show is the greedy algorithm, which is again what you would expect, but if you haven't seen it before, then it's not obvious what the greedy choice is. So again, we are given a set of endpoints and want to build a spanner. So we order the edges of the complete graph by lengths in non-decreasing order, and then each edge is considered, and either we add them to the graph or not. So we add an edge if the current current spanner does not contain a path of stretch vector t between the two endpoints. So the shortest edge is always added, and then in this example, maybe this would be an interesting question, that if our stretch is 2, do we add the 5th edge or not? And you say we don't, because there's already a path between the two endpoints of stretch up to 2. So this edge is, the next edge is added, and so in this example, we would get this graph out of the complete graph where t equals 2. So it's a straightforward generalization of Kraska's MST algorithm, and the nice thing about it is that it's a very simple algorithm. However, it's difficult to analyze. So that was one great achievement for Lee and Solomon, that they could prove that this achieves almost optimal lightness. So possibly optimal, but the upper and lower bounds don't match exactly, or matches up to lower order terms. So yeah, so one other thing I wanted to show of previous work is Steiner points. So this doesn't make sense in the abstract graph regime, but it makes perfect sense in Euclidean spaces, where, or in general, when there's an ambient space of some metric space. So apart from the given input points, we are allowed to add extra points in the metric space that as long as they help finding the shortest distance between the points. So an illustration of it is in the upper right corner here. So if the black points are input, then one can space them on the two lines so that depending on, or choose epsilon, so that the 1 plus epsilon spanner will be the complete bipartite graph plus a pass in the on each partite set. Right, so that will require that going between any two vertices on the top and bottom. If we take a detour to any other point, that would be 1 plus epsilon times longer than the direct edge. So, so the again, without Steiner points, the spanner would be the complete bipartite graph. But if we place via points somewhere in the median line, strategically, then actually the weight of the spanner drops, both the weight and the number of edges. So it's enough to connect both partite sets to these via points. So these are the current bounds on these spanners in Euclidean spaces. Roughly speaking, the exponent of epsilon drops to 1/2. Not exactly, but so I'm not going to say more about this regime, but I only point out that for sparsity there are tight upper and lower bounds, and for lightness they are not matching yet, but they're close. So it looks like that both in the without Steiner points, these upper and lower bounds match, and here for with Steiner points, they almost match. So what will I talk about today? So the topic as minimum weight spanners. So lightness is an important parameter that compares the weight of the spanner to the MST. It doesn't try to optimize it, it compares it to the MST. So the question I talk about here is the minimum weight for a given point set. So but let's see what we get from these tight bounds that we have seen in the previous slides. So we know that the greedy spanner gives a almost tight bound for the lightness. And this lightness bound is epsilon t minus the lower order terms. And so that compares the weight of the spanner to the MST. But for the MST, we also have tight bounds that was actually a lot older bounds. So for instance, if we have n points in a unit cube in d dimensions, then it's known that the weight of the MST is order n to the d minus 1. And the illustration is, so it's also best possible. That's what I'm wondering about. Is that
Is it like a random set of points in the cube or what?
Oh, agreed.
Just a grid. Oh, just a grid. Okay.
Is the bound, maybe this is off by some scaling factor, because so maybe it had to be scaled to the down to a unit cube, and maybe I didn't do that, but this is well known that grid is optimal, where the MST is just connecting adjacent grid points, and it's a classical result that it's asymptotically tight. So in the for the lightness bound, the tight lower bound was on the previous slide already in the upper right corner. So placing in 2 dimensions, placing points on 2 parallel lines. And so both of these lower bound constructions generalize to D dimensions. Here, this would be a gradient. This space, and here instead of 2 lines, we would have two hyperplanes on opposite sides and the grid on each. The point is that both of these bounds are tight, but the lower bound constructions are very different. So that suggests that if we put these 2 bounds together, we get an upper bound, but maybe that's not going to be tight. So this is what we get by combining these 2 for the weight. And the result I'm going to talk about in more detail is that one can improve it. So one can find a better bound for the weight. So compare, yeah, so let me go back to the previous slide. So this was the bound for the combination of the 2, and this is the improvement. So the improvement is only in the exponent of epsilon. The dependence of n is the same. And it's also clear that the improvement gets smaller as the dimension increases. So the biggest improvement is in 2 dimensions, from epsilon to the -2 to the -3/2. But the nice thing is that this bound is optimal. I can show the lower bound construction. That's just a combination of the 2 lower bounds. So that's the easy part. So here's the lower bound construction. Yeah, one place n points in a unit cube. How do we do that? So we partition the cube into epsilon to the d-1 times n smaller cubes and place this tight lower lightness construction in each cube. And then it's a easy calculation that in each of these small cubes, the lightness lower bound still carries through. So we need a complete bipartite graph between the 2 partite set. Via points in other cubes don't help, and then we just sum the weight. So that's an easy bound. And to talk about the upper bound, it takes longer. Any questions so far? So I talk about before I talk about the upper bound, there's another question. So the grid is not the lower bound construction, and that's surprising because in many of these geometric problems, the grid is often optimal. So you might think of crossing numbers or distinct distances. There are a large number of classical problems where the grid is just the worst or best case scenario, and here it's not. So, but how do we know that it's not the grid? Well, so that raises the question that what is the minimum weight of 1 plus epsilon spanner for the grid? And surprisingly, I don't know. So I tried to look up first that maybe it was studied a long time ago, and apparently it wasn't. And then I tried to prove something, and my bounds don't match. So these are the upper and lower bounds that I have. So there are 2 formulations for the problem. One way to with scaling or without scaling. So one way to think about it is just take the integer lattice, n by n section of the integer lattice, and then the dependence of n is just n squared. And the other setting is the same as the previous, that scaling everything down to the unit square. And then the same dependence on epsilon is the same. The only difference is that dependence on n is scaled down. So yeah, I'll get back to this as well. But let me just highlight this open problem that this should be it should be known by now, I think, that what is the best spanner we can have for a grid. Anyhow,
Well, is the upper bound easy? Like,
pardon me?
is the upper bound easy here? In this?
No. So the upper bound that I have is the algorithm that gives the optimal upper bound for, in general, applied to just for the grid. So it's not easy. But maybe that there is something easier for the grid. So I don't know. Yeah. So the other annoying part of this problem is that I don't know whether the upper or lower bound is right for the grid. So what is clear that it should be in this format, that the dependence of n is clear, and the only question is the dependence on epsilon. So to get some intuition, when we talk about the lower bound for the grid, and the lower bound I have is very weak, so I can prove that some edges are must-have, right? So must-have edges mean that every 1 plus epsilon spanner on the grid must contain these edges, and I give a lower bound for the weight of these edges. So, so there are two conditions. One is the empty ellipse condition. It means that if you have 2 points A and B, and this epsilon, a given parameter, then any path of length 1 plus epsilon times AB must be inside this ellipse of foci A and B, and as pictured. So usually for small epsilon, these ellipses are very skinny and long. So if there's no other point in this ellipse, then A and B must be connected. So there must be an edge in this spanner between them. So ellipses are hard to work with, and even in the grid. So an easier condition is an empty slab condition, that I just take the entire infinite slab centered about this point pair, and require that this slab is empty apart from points on the same line. So A and B are, of course, in this slab, and because it's a grid, it's periodic. So all the repetitions along the same line. But apart from this line, there shouldn't be any other points. And then the same condition holds, that if the slab is empty apart from this line, then the 2 points must be connected in this manner. So, so the lower bound goes like this: that if we just take some primitive vectors, then they satisfy the empty slab property. And which edges do I take? So we are working with an n by an integer grid, and I take primitive vectors where both coordinates are roughly epsilon to the 1 minus epsilon to the minus 1/4. And then it's an easy calculation that these primitive vectors satisfy the empty slab property, which is some volume argument. And then it's also easy to sum up their weight, and this is the weight I get so this is primitive vectors from the origin. So that means that the origin must be connected to all of these points in a spanner, and then if I translate this star to all other grid points, then I get this overall lower bound. That's so it's an easy bound. So possible improvements is one can show that there are other must-have edges as well, but it's not clear. Yes, one can find some sporadic examples that there are other edges that are also must-have, but it's not clear whether the sum of their weight is greater than this, and it's not easy to add them up. So where exactly they are. So that, yeah, so this is an open problem, how to improve. Questions about this? So yeah, so there's no question. I talk about the upper bound. So the upper bound is a longer story. So this is an algorithm that works for any point set, and then I will apply it for the grid as well. But let me start with another classical construction that's similar to the theta graphs. It's really almost the same, but it's called the Yau graph, and it's I think, yes, also goes back a long time ago. So similarly to theta graph, we partition the plane into cones from every point P. And the cones there are k cones, their angle is 2 pi over k. And this time we just find the closest point to P in every cone. So Euclidean closest point. So it's conceptually easier, but computationally actually harder. And then connect P to all of these closest points and do it for every P. So the same kind of proofs show that if the number of cones is 1 plus 1 over epsilon, then this is a 1 plus epsilon spanner. It generalizes to higher dimensions. So this is the basis for the algorithm I want to use, but I want to sparsify the Yau graph. So the basic idea is that perhaps we don't need 1 over epsilon cones. Perhaps we can use fewer cones. And this is the key idea on this slide. So suppose that P and Q are already connected. So there's an edge between P and Q. And now we are wondering whether we should connect this point P to another point B. So for instance, maybe this point B is in one of these cones, and the Yau graph would add the edge from P to B. But it turns out that in this setup, you might not need this edge from P to B, because if we already have an edge from P to Q, and we have a 1 plus epsilon pass from Q to B, then the combination of these two is short enough. So it's going to be a 1 plus epsilon pass from P to B. And the condition when this is possible is explained in the same picture. So it's based on these two cones. The cone of W1, I think it's W for wedge, but the angle of this cone is not epsilon, but square root epsilon. And so if you go back here, in the Yau graph, the cones of the angles of these cones are epsilon roughly. So there are 1 over epsilon cones, and each one has angle roughly epsilon. So here, this square root epsilon is a cone of a lot larger angle, right? So that's one key observation, and the other is that so this the shape of these two cones just guarantees this geometric observation. But this is what I want to use. And again, this is another illustration. So this is the overlay of the cones from the Yau graph. There have these epsilon angle. And if the Yau graph would add all of these edges, all of these dotted edges from P to these closest points in each of the small cones. But this observation just shows that we actually don't need any of these edges, because we can just use Q as a wire point. So so one more. So this is a technical lemma that the same observation works not just from P and Q, but it also works for nearby points. So if there are some other points nearby, then we can just use the same P and Q as a via point. So if you have some nearby point A, then we can still use P and Q as two via points for a path from A to B. So it has a very long proof, but the idea is pretty much the same as this. So now I can show the.
I have a question. So what do you need to assume about this nearby point A? Is it just that it's close, or you need to have a path in this?
Yeah. So here the assumption is that the question is the same. That instead of P, we draw. So the cones of the Yau graph are done for every point. So suppose that for point A as well, you want to draw these 1/epsilon different cones. And for instance, B is the closest point in one of the cones. Okay, so the Yau graph would add the edge A to B. But if we already have PQ edge in our graph, and if we already have by induction a 1+epsilon pass from A to P, and another 1+epsilon pass from Q to B, then the concatenation of these three things, so A to P, then a direct edge from P to Q, and then a pass from Q to B, these together would be a 1+epsilon pass.
So the induction, you call induction, the induction is on what?
So the induction is very similar to the greedy strategy. The proof that the greedy strategy actually works. The Yau graph has the proof for the Yau graph is the same proof that. So let me just. I had a slide about the greedy strategy, so I go back. I didn't have a slide about the proof why the greedy works, but the proof is basically by induction that. Yeah, so I don't have a slide for the proof of why it works, but one can just prove that actually yeah, so we can consider the edges in non-decreasing order, and for each of these point pairs, we'll either have an edge because we add the edge between them, or we guarantee that we already have a T approximation in the graph.
Okay, but what is the order? So here is the order of that you introduced the edges is clear.
Yeah, this is the order.
But what is the order?
Non-decreasing order of the point pairs.
But what is the order in this other algorithm in the Yau?
The Yau graph. The construction for the Yau graph is not ordered. It's so let me just go back to the Yau graph construction, which is right here. So it just and that's the nice thing about the Yau graph. It's for each point P, we draw these 1/epsilon cones and connect each one to the closest point. Do it for every point. And then separately prove that this is actually a 1+epsilon spanner. The proof why it's a spanner is by induction on the edge pairs. So induction showing that for any pair of points at distance up to x, the Yau graph contains a 1+epsilon paths between the two endpoints. So the base case of the induction is that the closest point pair is always connected because the closest pair will be one of these edges that are. So the closest pair is in one of these cones.
So the induction is on this X that you defined, yes?
So the induction on the point pairs ordered by lengths.
Okay.
And the end of the induction shows that between any pair of points, there's a 1+epsilon pass.
And now when you consider this And that you don't need to add all the edges.
And yeah, so here the plan is exactly the same, to use the same induction.
Okay.
And when we want to establish that, so the question is, do we need to add the edge AB or not? Then the Yau graph strategy would say that this AB pair is in the cone, so it must be added. But our induction argument would say that maybe it's not really necessary because we already have this a path between these two yellow points. So this path from A to P already exists by induction. From Q to B, there's a path by induction. One would actually have to show that QB is shorter than AB so that the induction hypothesis, so it was considered before. And then this lemma, this geometric argument shows that the concatenation of the three things is a 1 plus epsilon path. So this is actually, this lemma is a little stronger than what is needed because it leaves some room for error.
Yeah, you have just multiplier 1 with the PQ distance.
And maybe this is even points in the wrong direction. Yeah, so this is the wrong inequality. But yeah, so the right hand side should be 1 plus epsilon times AB. And I should say, but it doesn't say right here, that the concatenation of these three paths, so A to P, P to Q, Q to B, together is less than 1 plus epsilon times AB. And there's even room for error. Yeah, so ignore this inequality, it points the opposite direction.
But when you say that you use the induction call, so you already processed, you built some kind of spanner, but the spanner only serves the pairs that are closer, and now you're ready to deal with pairs of points that are a bit further away. And now you know that these edges, these long edges, this AB edge or this kind of, will never edit because they are too long. They are not necessary for these shorter, closer pairs, right?
Yeah, so the plan is to modify the Yau construction so that some of the edges are never even added to the graph.
Okay.
And then,
got it.
So it's going to be a sparser Yau graph, but the proof will be still by induction. So the same strategy for the proof, but with fewer edges. And this is so this is the actual algorithm. This is in pictures and in words as well. So instead of using cones of angle epsilon, so 1 over epsilon cones of angle epsilon, we use two phases. First, larger angles, so angle square root epsilon, and then this is on the left hand side, and then each of these square root epsilon angles are refined to the same angles as in the Yau graph. So in the first phase, when we look at the larger angles, we actually connect the point to the closest point in every cone. So this is the same as in the Yau graph, but with larger angle, so square root epsilon instead of epsilon. And then when we, on the right hand side, when we refine these larger cones, the smaller ones, we don't necessarily add all of the edges to the closest point, but only if this condition in this condition holds here. So if the points are inside this blue region, then we don't add the edge. If it's somewhere in this gray region, then we add the edge. So it's and yeah, the actual algorithm is a little more. So there's some ordering in each of these cones project. So consistent ordering for. So the extra step is that instead of doing this separately for each point, each center P, we can just compose a common list of all of these ordered pairs for every center to every point in this cone, and we add them one by one in this order. The idea is the same. So this step only matters later for nearby points. Yeah. So
process this. You want to process these pairs with respect to the distance because you do this induction call. When you'll do the long edge, you want to know if these short paths are there or not. So that's why I think you want to process in this order, right? No?
Yes. So exactly in this reminder, this pink area here, that want to make sure, so you want to use it for another point P prime or point A in this region. Then I want to know that there's already an edge from P to Q. But it's two phases, so larger cones and then subdivision into smaller cones. That's a relatively simple algorithm. So, and then that's the name of the algorithm, sparse Yao. So it's almost the same as Yoga, but some of the edges are just never added. Now, once we have this algorithm, there are two things to prove. One is that it gives the 1 plus epsilon spanner. So this is a proof by induction, as we discussed, and I'm not going to go over the steps. That's using those lemmas where the inequality was actually wrong in my slide. That's correct in the paper. And the other thing we need to prove that the weight is this quantity that was in the theorem earlier. If you run it for n points in the unit square, and the idea is to charge weight to area. So so it will be important that all these points are in the unit square, because then this charging scheme will charge against the area of the unit square. So I say more about this charging scheme and nothing about the induction. So this upper bound is broken down into 4 factors. So 3 factors of epsilon to the minus 1/2, and then square root them. So let me just explain each one of them. So this is just in the plane in higher dimension there. One of them generalizes to. So the number of cones goes up in the dimension. So this is all about the plane, 2D. So 1 factor of 1 epsilon to the 1/2 is the ratio between the 1 large cone and the small cones. Right? So the large cone has square root epsilon angle, and the small cones have epsilon angle. So each large cone contains epsilon to the minus 1/2 little cones, and here's the geometric observation is right in this picture. So if some of these small cones had a long edge, so the closest point was very far from P, then we actually don't add the edge. We only add the edge if the closest point is somewhere in this gray region. But in this gray region, the length of this edge, P to Qi, is actually at most twice as long as this edge here, P to Qi. And this P to Qi is the edge that we always have, because in the large cone, we always connect P to the closest point. So the weight of these edges in the small cones is at most square root minus 1/2 times the actual edge that we have. So that explains one of the factors, absolutely minus 1/2. And with this, we actually can forget about the small cones for the analysis. It's enough to prove that if in the larger cones, the total weight will be this much, absolutely minus 1 times square root 10. Okay. So what do we do with the large cones? So this will be a charging scheme from area, length to area. So back to one more observation here. So here, how do we get this edge P to Qi? So in this cone, Qi was the closest point to P. So that means that this section of the square or sector is empty. So we have an empty sector, P on one hand and Qi on the right hand. And for different points, P, these sectors are similar. So all these angles are aligned. So there are overall epsilon to the minus 1/2 different orientations. We can just do the calculation for each orientation of these sectors. So that explains another factor of epsilon to the 1/2. Right? So let's just focus on one orientation. So if these sectors were pairwise disjoint, then we would be in a very good position, because we could just partition the total area between the sectors and we are done. But that's not the case. These for different points P, these sectors can overlap. So each one is empty, but they can overlap. So one challenge is to bound the amount of overlap, how much they can overlap. And that's another, so that's one of probably key part of the charging scheme, that that we can bound the number of sectors that can contain any single point. So the so that at most so how many can overlap at any single point. So suppose that this blue X is contained in some number of cones. Then they all similar. So the edges of the cones form a terrain. So one would have to rotate it by 90 degrees to actually see it as a terrain. But what is clear from this picture is that this is a y-monotone curve with slopes of the same angle. And here is this important observation that for nearby points, we also erase so how to explain this, that when we added an edge from P to a point Qi, then we also don't add any edge from this nearby pink region to this larger blue region. That means that if this point X is contained in several different cones, that these apices, these red points, cannot be very close together. So there's a minimum distance between two of these apices. In other words, if P is one of the apices of the cone, then another apex cannot be in this pink region. And this gives a lower bound.
So I was thinking that now we are just counting the edges that were coming from these large angles, from this 1 over.
Yes.
Okay, and then didn't you say that these edges always go in?
They always.
So yes, but now, so this is why I'm lost, because now you say that when they are close enough, these points in the terrain, then, but they should be always in, yeah, and based on the algorithm.
Oh, but yeah, I think I skipped that stuff. But yeah, so if let's see again. Yeah, so they're not always added. You're right. That's so if we add an edge PQ in this list, then any other edge from this pink region to this blue region would not be added. Yeah, so this is a repeating picture in this lower right corner. That if you already have an edge from P to Q, that means that this PQ edge could be a via point. P and Q could be via points between anything in this pink oval and this blue region on the right.
So this distinction on these larger angles, like square root epsi, and smaller angles, is just in the analysis. In the algorithm, you don't make a distinction. You just go in the order of the length of the edges and then discuss if you put them in or not. Is it true?
Yes, that's so even these larger cone edges are not added if they're already covered by this this pink blue pair. Yeah, so order all of the edges in each direction, and yeah, so because what is this? Yeah, this is the list of ordered pairs. So that's they're ordered by decreasing order exactly to support the induction proof.
Okay.
And then when one of these edges is added, then any edge that would go from this pink region to the blue is just erased from the list because they're not. We know at that point that they're not needed. Yeah, so that's why there's no, if one of these PQ edges is present, then there's no edge from this pink region to the blue region. And that's what we use here in this argument, that in this y monotone curve, the vertices of the curve are separated by it. So if we talk about sectors of comparable size, then the separation between the vertices is at least something like epsilon to 1 minus 1/2. And yeah, so then that limits the amount of overlap. So yeah, so this is one step. So this assumes that these sectors have roughly the same size. And then one would have to say something about sectors, overlapping sectors of different sizes, but that's easier because these apices are, so even though the sectors can overlap, the apex is an actual point. And because the sectors are empty of points, none of them can be inside a sector. So even so that means that these colored sectors in the interior are always disjoint, and we can just count their areas instead of the core of the sector that are actually disjoint even if the sectors overlap. So this helps to bound the area of sectors of different sizes. And then we get the same bounding overall. And this is the last, so this is the slide for the area to length to area bound, which is just Jensen's inequality. So we have an upper bound of the total area of these empty sectors over for one fixed orientation, but all possible sizes. So summation of different sizes and different sectors. So the total area is this much. That was the previous slide. So what is the area of a single sector? Well, it has the center angle of square root epsilon. The radius is the length of the edge. And so after constant, this is the area. Square root epsilon times edge length squared is the area of each sector. And now Jensen's inequality gives changes the square lengths to just a summation squared, and then we just solve for the total lengths of the, so isolate the total lengths of the edges from this to get these bounds that we wanted. Okay, so in parentheses, this is just the average length of one edge. It was just the simplifying factor. So this was the upper bound proof. Other questions about this?
So the set Fi here is what?
Is the set of so all the edges that are added for cones of the same orientation. So R was the set of cones, and for each of these empty cones, there's an edge. Fi was just the set of edges.
Okay.
That correspond to the same orientation.
And then when you apply this for the grid, planar grid, you cannot.
Yeah, so that's that gives this bound. So so it's using the same algorithm, but then because this is the grid, we know a little bit more about how many points can be in each of these larger cones. So specifically, we have Fick's theorem. So that any triangle has area at most 1/2 in the plane, And yeah, so that's one key part. The other part is a bit of number theory. So namely Fourier sequences. So let's just suppose, so a grid is symmetric. It doesn't matter which point is the point P. So suppose that we draw cones from the origin, and and this Yao graph strategy draws cones at the origin and connects it to the closest points in each cone. Right? So we need to understand what is the distribution of these closest points. And for that, Fourier sequences are really handy. So the primitive vector is a vector where the two coordinates are relative prime, and Fourier sequences are exactly these ratios. So the slopes of primitive vectors. So typically it's set up only in 1/8 of the cone. So with the assumption that A over B when A is less than or equal than B, or up to N. So that visually that means that we have slopes between 0 and 1. So it has many fascinating properties that Fourier sequences have been studied in number theory for a long time. One result that is particularly useful for this analysis for this algorithm is the average distance of an arbitrary x to the closest slope in the Fourier sequence. So if x is an arbitrary slope, it's always closest to one of these slopes in the Fourier sequence up to n, and it's visually that. So this red slope is x, and then the closest one would be probably this blue slope in this example. Or if we lay out the slopes in a line between 0 and 1, that x is an arbitrary slope, and then there's a closest Fourier point, which would be this. So the theorem of Kargev and Zhigyarsky it gives an average value for this distance. So if we integrate over all slopes, then this is what we get. And we can use this. Yeah, so this is just really a sketch. So first, there's some distortion that we get by mapping slopes to the interval by using the tangent function. But the tangent in this range, in this 0 to 1 range, has bounded slope. So it's even though it's not a linear function, we can just take the worst case and we lose some constant. And what we have here in the Yao construction is that we subdivide. So we have 0 interval. This is the slopes from slope 0, so horizontal, to slope 1. So y equals x line, and this would be a subdivision into cones, into these intervals. And for each of these cones, we want to find the smallest element of the Fourier sequence that's in that cone. So the ratio between. So we are looking for such a point pair. So it's x coordinate, sorry, y coordinate p and x coordinate q that is in this cone. And of course, if every cone contains the closest grid point, so the question is that what is the size of n? So again, so this is Fourier sequences are parameterized by n. So we are looking for points up to n. So the question we have here is that if you are given our cone from the yellow graph, what is this smallest grid point, smallest n, where the Fourier sequence contains a point in that cone? And you can estimate that using the so the proofs of each of this is not on the slide, but
you want to estimate qi in terms of k, right? Or do I get it right? So for example,
yes.
It's obvious that you can have a denominator 2k, I think, because this goes exactly in the middle of your cone, right?
Yes, so I'm not to estimate the denominator. That's the...
And then, so what is the statement that qi is, how large is it in terms of k? Then it's...
Well, I don't know. I'm interested in this summation.
Okay.
Over all cones.
Okay, I see.
And that's related to, again, the proof of this lemma is not on the slide, but this can be related to the average distance of the integrals. And this one just comes directly from that theorem of the previous slide. So this slow down. And then how to get from a bound from the summation to this cube of the summation is just algebraic manipulation. So it's again.
Okay, I think I see, because from this obvious thing that I'm saying that qi is kind of, say, at most 2k, then the summation would give you k squared, right? And here you write that this is k to the 1.5, so this is better, and it doesn't look obvious, yeah. Mm-hmm.
No, it's a long calculation of almost a page to. But it's just algebraic manipulations, like working with sums.
Okay.
But ultimately, this is so this is actually interesting question on its own. What is the summation? But this is what is used for this geograph approach. And so proof of none of this is included in the slides. So yeah, I was trying to show a couple of ideas only. So for the upper bound for the grid is just use exactly this algorithm that we talked about, the general point set. And the advantage is that for this area between the two cones, so this, what is this area? Let me just scroll back a few slides. So this area of the set minus V1 or W1 minus W2, so this gray area. So this is the area where we actually add extra edges in the cone. And so the question is how many edges might be added here. So in the worst case, this was just epsilon to the minus 1/2 factor. If in each of these cones there's a point, but for the grid that depends on the area of this region. So by Pick's theorem, we can't have more than twice the area number of grid points, and that's slide going back. There's this here. So we get a better bound for that area. So this is just this, yeah, and that's why if we sum over the edges, we get yeah. So instead of adding a factor of epsilon to the minus 1/2, we get this formula for the number of grid points. So there's a constant epsilon to 1/2, and then the edge length cubed. So this is the cube that works into this cube. So then we need a summation of these cubes over all the cons. The notation is not really great. It's here QI is a point where this QI is just a quantity. It's the denominator only. It's not the same QI. But this is just the length of estimate for the length of the single edge. So I have more slides for online algorithm, but I am afraid I don't have time for that. So skipping a whole bunch of slides about online algorithms. Think or should I talk about it?
Well, I don't know. I mean, I don't know the online setup at all of this problem, but we can give the setup. Just maybe don't go into results or techniques, but just what is the problem? Yeah.
Okay, so it's good to know what the problem is. So if you have seen online algorithms, then you probably already know what's going on. If not, then here's the setup. So our input is a sequence of endpoints, and they're presented one by one. And our algorithm has to maintain a t-spanner. So t is also a given parameter. You need to maintain a t-spanner for the first I points at all times. And then additional condition is that the algorithm can add new edges, but it cannot delete. So that's one key difference from dynamic algorithms. So dynamic algorithms can update the spanner, can add or delete. The online algorithm can only add. So this is a very small example. 3 points arrived, and this is still a two spanner. We don't need a edge from S1 to S3. Here for 4 points, this would be an online spanner, but this is not the optimum spanner. This would be an optimum spanner. So the performance of online algorithm is measured by comparison to the optimum, the offline optimum for the same set of points. And this is called the competitive ratio. So there's a weight. In this case, we care about the weight of the spanner. So the algorithm computes a spanner of a certain weight, and the same input has an optimal weight for the 1 plus epsilon spanner, and we take the worst case ratio over all input sequences, finite sequences. So this was already yeah, so one comment about this that is usually a difficulty for these online algorithms, that for some problems, when you add new points or the input increases, the optimum can only increase. That's not the case for the Steiner-Spanner, for this Spanner problem. It's related to Steiner points, but it's without Steiner points. So it's possible that a new point arrives and the weight of the optimum goes down. This is one example. And the relation to Steiner points is that if the Steiner spanner has lower weight, then the adversary could just add the Steiner points, and then the weight goes down. So that's just a way to construct something for the adversary. So there's a lot of work done on MSTs and trees, but no previous work on non-perceptual spanners. And I talked about dynamic algorithms already. So dynamic algorithms can add and delete edges. And the other difference is that dynamic algorithms don't care about the running time or update time. So here for online analysis, the update time doesn't matter. The key parameter is the competitive ratio. And then, of course, it has also Steiner point version, where the algorithm can add Steiner points, but also cannot delete them. And so these are a bunch of results I talk about, depending on time. So for instance, we have a tight band for 1 dimensions, and not so tight in higher dimensions. So do you want to see 1 dimension?
Yeah, I was about to suggest, let's maybe do just a one-dimensional line and.
So 1 dimension, yes, probably that's the least geometric result in my slides. So 1D is just a set of real numbers. So this is what the adversary would do. This is the lower bound construction. So what is the goal of the adversary? So the adversary wants to fool the algorithm to add many edges that are actually not needed for the optimum. What is the optimum for 1 dimension? Well, we have endpoints in the line. Optimum is just a path. So optimum is always just a path, varying from the leftmost to the rightmost. But the adversary can fool the algorithm. So this is what the adversary would do. Would put down these leftmost point, rightmost point, P node, Q node, and then they have to be connected by this orange edge, right? The algorithm has to maintain a spanner at all times. Then the adversary adds point P1. Now, it has to be connected to P node for sure, but it also has to be connected to Q node, because using a detour, so P1 to P node and then to Q node, would be more than 1 plus epsilon times the Q distance. So, and then this argument repeats. So for P, adversary adds P2, it has to connect it to both left and right. So all of these long edges all the way to Q node have to be added. And of course, none of them is needed. The optimum would be just a pass from all the way from P to node. So this gives one lower bound of roughly 1 over epsilon. But then the adversary can repeat it, the same strategy in each of these arcs. And then this is the lower bound we get for fixed epsilon, and n goes to infinity. Now, what is surprising, and yeah, for me it was surprising that this is optimal, and this, so that there's an algorithm I can explain. The analysis is longer. It's not on the slide. That so the algorithm maintains a path from. So the algorithm has to maintain a 1 plus epsilon spanner at all times. This spanner will not be a path in general, but on top of the current spanner, the algorithm also maintains an X monotone path between the leftmost and rightmost. So we need to tell what to do when the new point arrives. So the easy case is if the new point is left of all the previous points or right of all the previous points, then we just connect it to the closest point and update this X monotone path to include that as well. So the interesting case is displayed on this figure, that the new point somewhere in the middle. And there are two cases. Yes, there are three cases basically. So it's always, this new point is always contained in one of these edges in this path that was mentioned here. And we have three possibilities based on the endpoints of these edges. So if the new point is very close to the left endpoint, then it would be added to this cluster. Right? So the idea is that if this is a small cluster very close to P, then we can have a path from this cluster to anything here going the long way, so making a detour. And this is still 1 plus epsilon times the direct distance. And the same happens on the right side. But if the new point is somewhere in the middle, it's not close to either of the endpoints, then we just add an edge to both sides. And if this happens, then this X monotone path has to be updated. So instead of this edge, you would have to have these a longer X monotone path. And basically, this is the expensive step when a point is connected to both left and right.
But then if you add this vertex to this path, you don't know if you don't know the structure of the thing that was close to P or close to Q. So
yes, I know that's what I mentioned, that it's a non-crossing spanning. So there's no non-crossing in 1D just means that this is a laminar structure. So the edges are all contained, proper containment between them. So this laminar structure helps for the analysis, as we know that if this long edge was present, then none of the other edges cross, and there must exist a new path from P to Q.
Yes, that's nice. That's nice.
And the analysis is not on the slide, and so the difficult part is to handle properly these clusters on the left and right. So if new points arrive here somewhere, then you still add it to this cluster. It still adds weight, but it has to be kind of amortized into some geometric series. And the case where these points arise in the middle and it's connected left to right, that comes with a lot of weight, but that actually is necessary. So the lower band shows that happens occasionally. And the other slides are about higher dimension. That's also very interesting, but I want to. I think I'm used up my 90 minutes.
Okay, so let's thank the speaker. Thank you, Csaba.